Our speaker tonight is Silvia Bonoli. Silvia has her PhD from Munich in astronomy, and gradually through her career, as she's wandered around the world doing astronomy of larger and larger objects, she's come more and more to the frontier of the most energetic objects in the universe. And that's what she'll talk to us about tonight. Black holes and their interaction with galaxies, a love-hate relationship. So Silvia, please.
Thank you.
Please excuse me. There was one more thing introductory that I had to say. I told you some time ago that this auditorium was going to be demolished. And it will be demolished, but fortunately they keep pushing back the date. So I think we're good in this room through the July and the September public lecture. And after that, we're just going to keep scheduling them until they bring in the bulldozers. So just keep an eye out, and we hope to see you here in July and for the coming lectures. Okay, thank you very much. Let me turn it over to Silvia.
All right, thank you, Michael. I want to, first of all, thank the Office of Communication at SLAC for giving me the chance to give this talk tonight. They've been very supportive in organizing the event, in making a very beautiful image for the poster. And yeah, so tonight we're going to explore the relationship, this love and hate relationship between black holes and galaxies. I'm not going to talk about particularly fancy things. I'm just going to briefly touch upon some issues that relate Einstein and general relativity. But the black holes we're talking about tonight are relatively simple. But still, it's pretty amazing what we know about them and what scientists have been able to find in the last 100 years, starting from essentially not even the idea of a black hole, to the point where we are today, that we really know that black holes exist, and they're a really important piece of the puzzle of our understanding of the whole universe. I thought about starting this talk by giving you a very brief introduction about myself and by my trajectory around the black hole, and what brought me here. I started undergrad. I grew up in Italy, as you probably got from my name and my accent. I started university there. I studied astronomy. My initial idea was to study archaeoastronomy, eventually to keep doing research in that, so study what the ancients knew about astronomy. I found that quite fascinating when I was young. But then I realized that actually I was more interested in looking forwards rather than somehow looking backwards. So I decided to go on in research. So Bologna is one of the oldest universities. We claim it to be the oldest university in the world. I think in about 70 years, 75 years, it will have its 1000th anniversary. This is an image of a building that is still there. This is, I think, a medieval image. Actually, I'm not sure from which year this is from. But this is the Observatory of the university in medieval age, where actually there were very interesting instruments, and now it's a museum for astronomy. So if you ever happen to go there, it's quite an interesting place to visit. And interesting people, like even Copernicus itself, taught at the university. Well, anyway, after Bologna, I moved for a master to Toronto in Canada, where I started working more on galaxies and also black holes and their dynamic interaction. I really liked it, enjoyed it, but decided to move on for the PhD in Germany at the Max Planck Institute for Astrophysics in Munich, where I met also my partner, who is here, also an astronomer, is particularly interested in cosmology, and later if you have questions about that, dark matter and dark energy, you can ask him. Then I moved to Zurich for a postdoc, and we had a kid who is now 2 years old. She's not here tonight. We spared her. And she's getting very good at traveling, following us, and also getting good with languages. Then we came here in September for a research position here at Stanford, working at KaiPAC and SLAC. And it's been really nice, but actually we're leaving soon. Next week we're moving to Spain for a new position, hopefully permanent. in a new research institute there. So here I just want to give you a trajectory. I started working on galaxies here, and I kept more and more being involved in black holes and getting more sucked into black holes. So, well, okay, let's start. Escape velocity. What is the escape velocity? So I would ask you, but not all of you, maybe the kids. There is here, I think, a very cute kid. Well, what happens if you jump? If you jump, you will come back to Earth. Why? Because there is the gravity of Earth that is pulling you back on the surface. So what is escape velocity? That's the velocity that you would need to escape an object that is gravitationally attracting you. For Earth, you would need to travel at 25,000 miles per hour to escape Earth. In the Moon, you need much less. It's a much smaller object. You would need only 5,000 miles per hour. In the Sun, the work gets much harder. You would need 1 million to go at 1 million miles per hour to escape the Sun. What is the object from which the escape velocity is equal to the speed of light, which is the maximum speed that anything can reach? This object is a black hole. The idea of something, of an object whose big mass or big density could be so strong that not even light could escape, was introduced by John Michell in 1783. He had this hypothesis of dark stars. He said, what if a star at the same density of the Sun, but 500 times larger radii? So you just imagine a sun, but you give it so much more mass that is huge. And you could imagine an object that is so big that not even light could escape because its gravity is so strong. Or equivalently, you could shrink the mass of an object to such a small point that even in that case, not even light could escape. In fact, we could become black holes. The Sun could become a black hole if it was of a radius of 1.8 miles, and the Earth could become a black hole if we shrink it to 0.3 inches in radii. So you can get a black hole either by making something which is really big and massive, or making something that concentrates a lot of mass into one single point. So let's go a bit through history briefly, the last 100 years, the research on black holes. It all started, well, the modern concepts of black hole all started by this guy, Albert Einstein. Most of people think of Einstein as this old man with crazy hair. I actually like very much this picture of his when he was 25, which is when he introduced most of his amazing revolutionary ideas. In 1905, when this picture is from, he introduced special relativity, and then in 1915, general relativity. And then in 1915, in the same year, Schwarzschild made the first theoretical description of a black hole. So he solved Einstein's equation to describe what is the gravity around a point mass, a sphere of mass. The difference between the two, they were both German, but Einstein was a pacifist and escaped Germany to avoid military service, whereas Schwarzschild was actually quite nationalist, and he actually joined the army in World War I, sorry, even though he was already 40 years old and actually died from an illness taken from the front. Likely Einstein was pacifist, so he kept doing great discoveries for many more years. So another revolutionary step was taken by Oppenheimer, another physicist, and I also like very much this picture of Oppenheimer because he looks like a Hollywood star. And so he introduced together with other physicists, the idea that a neutron star, which is the final product of a star after a star has died, and we'll come back a bit to that later, a neutron star which is above 3 times the mass of the Sun will not be able to sustain the gravitational collapse, will not be able to sustain the pull of the mass because of gravitational force, and would actually most likely collapse into a black hole although at the time still the name black hole did not exist. The term black holes actually came much later, in '67, when for the first time Wheeler, another important physicist, introduced the term black hole in a lecture. And of course it caught on right away, and from that moment on people started talking about black hole. It's indeed a very fascinating name. It was quite interesting because, astronomers tend to talk about very weird things. In everyday life, we talk about black holes, galaxies, dark matter, dark energy, as if they were bread and butter. But actually, it's very interesting how much effort from very, very smart people took to actually get to the point we are now. So anyway, let's get back exactly what a black hole is. So a black hole is a concentration of mass. We don't know exactly what happens inside a black hole. What we know is that the equations, Einstein's equation, predict that there is a singularity at the center. It's a point where all the mass gets concentrated to an infinite density. And then the black hole is defined by its mass, which defines what is somehow its size. So there is a surface on the black hole, which is called event horizon, and nothing that enters this point can ever escape. This is the point at which the escape velocity that we talked about earlier is equal to the speed of light. It was called event horizon because we cannot see beyond it. It's an horizon. And then black hole can be described with a spin, how fast it rotates, how quickly it rotates. So this is a sketch of how a black hole is, but actually, what does a black hole look like? If you just take a black hole, that would be its picture. You cannot see it, nothing can escape from it. So then, how do we know that black holes actually exist? Well, luckily enough, black holes like to get bigger. They like to eat. They like to get whatever is around them. And this takes me to introduce this concept that we call accretion. So you can think of it as, well, this is, I guess you can all recognize, this is a sink. You got water whirling, got water falling into this hole in the middle, and as they get closer and closer, they start spiraling in faster and faster. It's a bit similar what happens around a black hole, what happens to a black hole that has something around it, some gas or dust. This is an artist's conception, it's not really a picture. We cannot yet get such a nice picture, but it's an artist's conception of what could happen around a black hole. You have gas and dust around it. Also, the color is not really right, it's not necessarily blue, but it's just to give you an idea of what it could be. You have a black hole at the center, and then you have a lot of stuff around it that is getting into the sort of disk and starts spiraling in, and as it gets closer and closer, it starts spiraling faster and faster. And so what happens there is that, as things get closer and closer, it's a bit like friction. When you rub your hands very quickly, the hands get warm. So that's somehow what happens in the particles and in the dust that is around the black holes. They all collide with each other, like hotter and hotter, and they move so fast. They get really hot, and they start glowing. They start emitting light because they get so hot. And this light is so energetic that it can be seen we'll go to that in a second, and X-rays or gamma rays, which are the most energetic, and is the most energetic type of light that we know. Actually, I'm getting to that now. This is just a sketch of how the forms of light that we know. So photons travel like waves, and depending we call it the wavelength, what is the pattern of this wave, it can be more energetic if it moves faster and faster, or it can be slower, right? So you have the most energetic photons that are called gamma rays, and the least energetic ones are the radio, the ones that are used for radios. The visibles, the only type of light that we can see, it's actually a very tiny fraction of all type of light, all kind of lights that exist. Actually, we cannot see all this light easily. So only this type of light reaches Earth. So we have the normal telescopes. These are actually real images of real telescopes that can see the light in the classical way, the normal telescope that we would have if we go out and watch the moon, look at the moon. You can also look at the radio. The light coming from the sky that has radio energy can also be seen from Earth. But other types of light, especially the most energetic ones, luckily don't get to us. They are protected by the atmosphere. So in order to see objects that are emitting light of this kind, we have to go to space. And it's only been in the last 50 years that scientists have been able to build satellites that are able to look at this kind of light. So these are actually satellites currently taking images of objects that are emitting at those very high energies. So it was in 1964 that one of these first X-ray satellites identified in the constellation of the Cygnus, identified one source that was very, very bright in X-rays. And scientists at that point didn't know what it was. They knew, though, if they just look with a normal telescope, with just an optical telescope, so just the light that we see, they knew that it was very close to a normal star. So then scientists started thinking that this could actually be the picture describing what they were seeing. You have a star, a normal star that you see, and next to it you have a black hole that is accreting gas that is sucking from this star. This black hole is taking away gas, material from the star, and it's eating it with this accretion disk. And the light that we see in the X-rays is the light coming from this accretion disk, what we call an accretion disk. So this was a nice idea, although physicists were a bit skeptical. For a long time, physicists just thought that black holes were just theoretical ideas that actually didn't exist in nature. To the point that two great scientists, Stephen Hawking and Kip Thorne, made a bet. It was more of a joke. They made a bet. Stephen Hawking said, I don't think that this is really a black hole. I don't think that this is what we think, a black hole that has died after the life of a star. I don't think that this is a black hole growing. I guess some of you have gotten to to what they actually bet. Yeah. Stephen Hawking bets 1 year subscription to Penthouse against Kip Thorne 4 years of Private Eye. I'm not really familiar with these magazines, but I can guess what they are. Yeah. So, yeah. So eventually what happened? After years and years of more studies of this source, eventually in the 90s, Hawking gave up and he declared that he lost, because more and more evidence came that this object is indeed a black hole. The only explanation we have for what we see is a black hole. Yeah, so just to give you a quick idea, these are what is called stellar mass black hole. They are black holes that are about the size of a star, because they come from stars. So most black holes, so this is a star, stars as we know them, an average mass star like our own sun, eventually gets bigger. It in most of its life is just radiating energy by burning hydrogen in its center. Hydrogen burns into helium, and eventually it will evolve, and it will die when it doesn't have more fuel to power it. It will die like a white dwarf. A more massive star will eventually end up in a more compact object, which we call neutron star, which is a very compact object. But if the star to start with starts with a lot of mass, if you have a really big star, eventually this will actually die as a black hole, because we don't know, there is nothing in the current physics theory that could explain anything actually being able to resist so much gravity trying to get things together. So these are what we call stellar mass black hole. They're actually small black holes, even though they're pretty big. They're more than 3 times, 4 times the mass of our own sun. But in astronomy, they're considered the small black holes. The universe is actually pretty big. we have many stars that we can see that make our own galaxy, but actually the universe is full of galaxies. So our own galaxy is about 100 billion stars. The whole universe is maybe 100 billion galaxies. So the universe is big. There are many galaxies of different kind. There are some galaxies like this one, although sorry, it's not very clear. It looks more like a spiral. Some other galaxies that are more puffy. They're more like a ball. What happens if we actually look very far away? Again, in the 60s, Martin Schmidt was an observer. He was looking through this Palomar telescope, Palomar Observatory, which is an observatory run by Caltech. And he saw a source that looked like a star. He was looking at this telescope, he saw something that looked like a star. But when he actually examined more carefully the light coming from the star, he realized that it was quite strange. It wasn't quite what we expect from a normal star. He realized, after a long study, that this was not a star, as we see many others coming from our own galaxy, the Milky Way, but it was actually something that was much, much further away, much outside our own galaxy. So he discovers that there are things very far away, and it was the object furthest known at that time. But it was so luminous, you could see it as bright as one of the brightest stars. So then people started wondering what could actually make something that is so far away so luminous. And this actually was a great discovery, so he got the Time magazine cover in '66. And people then started to look at it more carefully, and he started calling this object quasar, because like quasi-stellar objects. This is again an image of this object. Now we have more detailed observation. We can also see what we call a jet. And now the only explanation for this such great amount of light is the presence of a black hole, of a very, very big black hole that is accreting a lot of gas. Now we have more evidence of this. This is another image of one of these objects called quasars. It's just a point here, but actually if you really look at it carefully, it is a lot of light, but it's coming from really far away. So we call those, generally, active galactic nuclei. So what is here, so to give you a better idea, this is a galaxy, a big galaxy, that has as its center a black hole, a really big black hole that can be millions or billions of times the mass of our own sun. And this black hole is accreting a lot of gas, is sucking in a lot of gas, and emitting a huge amount of energy that is letting us see this object really far away. This is another schematic view of actually, we generally call this object active galactic nuclei. So the nucleus of a galaxy that is active, because it's active, it's actually doing something. And this is at the very center of a galaxy. And depending to which angle we see the very center of the galaxy, we can just see the disk, this disk, or we could see, for example, if the jet, this jet that is produced from particles that gets accelerated at very high speeds, we could actually see directly into the jet. And we see really energetic particles that are pushed away from the center of this disk. So let me show you some other really beautiful pictures. This is a galaxy very close to us, which is called Centaurus A. This is what this galaxy looks from a normal telescope, in the visible light, in the optical, from a normal telescope as we know them. If you look at this galaxy in the X-rays with the satellites that are outside the atmosphere, you would see this galaxy looking like this. So it's very different. You see this very bright center and these very strong jets that are emitted and lights and lights and light years away, really far away from the very center. If you look at another type of telescope, and a telescope that looks in the radio, you will actually see something like this. So again, you see the center, and you see this jet that is interacting with the gas that is in the galaxy, creating this, how would you call it, a butterfly sort of shape. And if you combine all those, this is what you would get. If you were able to have a telescope that could see all types of light, you would see something like this, really amazing. So this is a galaxy that has a black hole at the center that is very active. This is the active black hole, massive black hole that is the closest to our own galaxy. And this black hole is about 10 million times as massive as our own sun. So it's really a big object. But let's look at things a bit in perspective. So if a galaxy, just to give you an idea, was the size of Earth, the black hole that is inside it, this very massive black hole, would be only less than 1 inch. So these objects are huge. These massive black holes are really big, but actually in proportion to the galaxy, they are fairly small. And yet, despite being so much smaller than the galaxy, think about 1 inch, an object that is 1 inch compared to something that is as big as the whole Earth. But despite this huge difference, the black hole is so powerful, a black hole is able to generate so much energy that the light from it, or from the gas that is around it, not really from the black hole itself, from the light that is around it, could outshine the entire galaxy. Just to give you a very brief idea, a black hole, if we want to extract energy from a black hole, we get an efficiency that is about 100 times higher than the efficiency we would get from a star, from the energy that we can get when a star is burning or when a nuclear reaction, as we know them, also as we try on Earth, are able to produce. So black holes, as we know them, are the most efficient way to create energy. Because, again, their gravitational pull, the gravitational force around them is so strong that the material is really heated up to really strong energy, to really high temperature, millions and millions of degrees. This is another beautiful image. This is actually a cluster, a collection of galaxies. This is what you would, how it looks from a normal telescope. Actually, this is a Hubble Space Telescope, one of the best telescopes scientists ever made. It would look like a collection of galaxies. Each of these points is a galaxy. If you look at it in X-ray, you would actually see this fuzzy light. And in the radio, you would see again these jets. And these are actually extending even further away than the galaxy itself. This, again, to just give you an idea how energetic, how much energy you can get out of these black holes, of gas around black holes. And actually, this is a sketch of the evolution of the universe, starting from the Big Bang down to galaxies where we are now. So these are the first stars, when the very first stars were born, about 400 million years after the Big Bang. Now our universe is about 3.7 billion years old. We can see quasars, and we'll come back to that again. We can see the light from black holes that are accreting, that light that was emitted when the universe was about, at this point, was about 700 or 800 million years old. So when the universe was really, really young, there were objects, there were black holes that were generating a lot of light, and that light had traveled for 13 billion years until us, to get to us. So we see this light that was created 13 billion years ago. And it's because it's so energetic that we can see it still now. So one question though, most galaxies are actually not active. So we've looked at active galaxies, galaxies that have a black hole, and now we know that they emit a lot of light, and we can explain that light only with a black hole at the center that is accreting a lot of gas. But many galaxies that we see are not that active. They don't have this central, what we call a central engine that is producing so much light. So the question is, do they also have a black hole? Well, the best example is our own galaxy, the Milky Way. Our galaxy is pretty calm. There are stars. at the very center. This is an image from a telescope in Chile, an image of the Milky Way. We see it a band of light. That's why it's called Milky Way. And there are many stars at the center, but there is no sign of activity. There is not a sign of black hole. So the question is there a black hole there or not? This is just to give you an idea. These are, if we could fly out of our own galaxy, that's what it would look like. It would be like a spiral. You have at the center higher concentration of light. It's just from stars. Our own solar system is out here. We're in the periphery, in the suburbs of our Milky Way, of our galaxy. And that's why we are in this disk, in this spiral, and that's why we see this band of light on the sky. And so the question is, what if we look at the center? Let's try to look at the very center. Astronomers have been trying to look at the very center to see if they see any sign of a black hole. This laser is pointing, doesn't get to the center. It's just pointing where the center, indicating where the center is. So let me show you a nice video that was made by some people at ESO, the European Southern Observatory. This is just zooming in from the image that we know from real telescope, trying to zoom into the very center. We first see images in the optical light from normal telescope, but as we go close to the center, astronomer needs to use infrared telescopes, so telescopes that look in the infrared type of light to penetrate all the dust that is in the center of the Milky Way. And you see these, actually astronomers in the last 15 years have been able to see these stars moving around. This is now an animation of these stars, how they move at the very center. It's amazing that now with the telescope of the technology now, astronomers can look at the very center of our galaxy and see what happens and see all these stars moving around. This is about 30,000 light years. So it would take light 30,000 years to get there. And this is an artist's conception of that there is a black hole in the center. Let me show you another animation that will be a bit more clear. Astronomers have been able to look at stars as they move in the center. And they've been able to trace their trajectory around the very center of our galaxy. And they've found that they move, now it will start again, that they move around the center in perfect elliptical orbits. Now after 15 years of observation, the orbit of one star has been all traced, have been all observed by astronomers. The first observation started in '92, and this star has been moving around and getting faster and faster, and then here we are in 2012. The observations of astronomers have been able to trace a full trajectory, and it looks a bit like the trajectory of a planet around the sun, around a star. But what it actually is the trajectory of a star around an object that we cannot see. But the only way this trajectory is in such a small place, actually this trajectory is about as big as the trajectory of Mercury around the sun. So it's really a small area if you think about it. But the speed of this star is so high that the invisible object that is at the center has to be 4 million times the mass of the sun. And this is the best evidence that astronomers now have for the existence of a black hole. There is no other way to explain so much concentration of mass, invisible mass, in such a small region. So, yes, so our galaxy has a black hole, which is pretty big. The black hole doesn't have much stuff around, so it's not accreting. It doesn't have this disk type of things. It doesn't have all this violent activity going on, but it's there, and we see its effect by the motion of the stars that are around it. And we'll come back to this black hole later at the end, because actually there are some surprises coming up actually in the next few years. Let me just first briefly summarize what we've said until now. We started on historically by giving a description of how scientists start to think about black holes, what led to the idea of a black hole, or a black hole somehow looks like. But now astronomers are evidence that black holes exist. These stellar black holes, smaller black holes, there are many. Astronomers think there are millions in our own galaxy. They are far enough away that we are not going to disturb us. They're not going to bother us. We're safe. But there are many around our own galaxy. But in other galaxies, there are big and much bigger black holes. These supermassive black holes. There are, in many galaxies, they can be very active and be very visible in such energetic type of, giving up so much energetic type of light, or they could just be quiet. They're not eating, they're in a quiet phase, they're taking a nap. And we see them, we just see them because they have a very strong gravitational effect around them. Now, 20 years ago, well, after these first active galaxies were discovered, then astronomers started to look more and more, also start looking nearby galaxies, in the quiet nearby galaxies, to see if this gravitational effect could be seen. The observation cannot be as good as in our own galaxy because it's closer, but they can still give good idea, good estimates of how big the black hole is. And astronomers in the last 20 years have actually, almost 20 years ago, they discovered many black holes indirectly, many black holes in many galaxies around, and they actually found that there is a very tight relationship between black holes and galaxy. So the bigger, this is just a diagram showing you the mass of a black hole. As you go up, the mass gets higher, and of the black hole, and as you go on this direction, the mass of the galaxies gets bigger. They found that there is a relationship between the mass of the black hole and the mass of the galaxy, in the sense that the bigger the black hole, the bigger the galaxy it sits in. And this relation actually is not the whole mass of the galaxy, but specifically the puffy, ball-like component of a galaxy. We have galaxies that, as we said before, they just look like big balloons. Other galaxies that look more like spirals, but they could still have a sort of what we call bulge at the very center. And the black hole seems to have a very strong relation with the mass of this puffy component. It's not, the relation is that for the black hole, the galaxy is, this puffy part of the galaxy is always 1,000 times bigger than the black hole. And this relation, it's always like that. Every galaxy that you observe or you find a black hole, the galaxy, this puffy part of the galaxy is always more or less 1,000 times the mass that is estimated for the black hole at the center. So astronomers started wondering, how is that possible? How does this so strong, tight relation comes up? At the end of the day, the black hole is much smaller than the galaxy. So how does the black hole know how big the galaxy is? How does the galaxy know how big the black hole should be? So the main question is, was this relationship always there? When was it established? And ultimately, it brought to the question, actually, where did this black hole come from? Did galaxies and black hole were born together at some point of the universe? Or did one come first before the other? It became sort of a chicken and egg question. Who comes first, the black hole, the galaxy? Who knows about what? One of the first leading theories about this is the fact that black holes grow when galaxies form, when galaxies get shaped. Or somehow the same process that creates a galaxy or that creates this puffy part of the galaxy is the same process that gives food to the black hole. So here we have a galaxy that is pretty quiet, it's puffy, and we have a galaxy that is very active. We have a black hole that is eating a lot. So how are these two things related? Could this be the final product of this phase? So one of the physical processes astronomers know that create this type of galaxy is the encounter of two galaxies. If you have two galaxies, for example, of a spiral type, that smash with each other, get together, the final product will be a galaxy that will look like this. So the idea is, will it be possible that during this event, actually, the gas that is in these two galaxies gets to the very center, gives a lot of food to the black hole, so that the black hole grows to the mass that we see today, and at the same time, the galaxy is formed. So that somehow you establish this relation. These events of encounter between galaxies happen a lot in the history of the universe. This is a visualization actually done, a simulation done by people here at SLAC. This is just putting some physics in a computer and see what happens. These are galaxies simulated in the computer, and they are evolving, and as time passes by, for example, this one gets encounters with this one, they exchange some gas. Now these two get together, they start sort of dancing one around the other until they get together, and finally they form one single thing. Yeah, we can look at this till the end, and this event happens a lot. In the whole history of a galaxy, it will have had many, many encounters with other galaxies. Let me show you another simulation that gives you a better idea of this. Again, this is something run in the computer. Actually, this is something that was done by my PhD advisor. Again, with the physics, we know you put the physics in the computer, you write some codes, and you see what happens. And this is an image of the stars in this simulation. In the same simulation, you also look what happens to the gas. Let's first focus on this. You have these two galaxies that are getting together, and then eventually they get closer and closer, they dance around with each other. They do a bit like humans when they get together, when a couple get together. And eventually they form one single thing that looks like these puffy galaxies we saw before. Now this thing is going to loop again, it's going to start again. Oh, this other side should start too. Let me go back and restart it like this. Now let's look at this. Now this is just looking at the gas in the same galaxies, what the gas does. Here now again we see the gas that is moving. But now in this simulation, both galaxies have at the center, they're also simulating what happens if there is a black hole in the center of each galaxy. We know enough physics that we can put in those simulations what would happen if there was a black hole. Now the black hole here gets a lot of gas and they start shining, do you see? And they start expelling a lot of material. And their energy becomes so strong that they get out, they expel a lot of gas. Because in this process of accretion, they get out so much energy that the energy they expel, the light, these particles that are ejected to very strong speed, are able to push away all the gas that is around. This is not, these are nice videos, but actually we know that these events happen in nature. These are actually real images, beautiful images from the Hubble Space Telescope of galaxies that are about to encounter, to get together. And so what would be this relationship, this love and hate relationship between a black hole and the galaxy? When two galaxies get together, somehow in this driven love, this love that is driving this encounter, they push a lot of gas to the center. There's a lot of gas that is going in the center where the black hole is, and the black hole lights up, starts eating. But then at some point it gets full, and it emits so much, then it has emitted so much that it says, it's enough, I don't want to eat anymore. It expels energy, and it pushes away all the gas that is around. That's how somehow I call it hot, love, and hate. It's a simplified way to look at it. So this theory that somehow is when two galaxies get together, that this active event takes place, has been tested a lot, not only by this kind of simulation, but you can also look at the statistics. How many events you have in the sky? Could we actually in our computer reproduce so many events, and with this certain distribution in the sky? A similar thing has been done for galaxies. This is the distribution. Okay, let me explain this. give me 1 minute to explain this. So on this blue is, we are here. In this blue is the light, the distribution of galaxies going back in time. When we look at galaxies, we know where they are, how far back in time they are, how far away they are. So this is how they are distributed in the sky, how far back, and this is just looking at the plane of the sky. And this is an image of what is actually coming out from simulation. So we know physics of how galaxies form, of how all structures in the universe form from more or less the epoch of the Big Bang, and we can put what we know about it in a computer and see if what's come out looks right, looks like the observations. So astronomers have been done this type of things to see what we know about the physics of the formation of galaxies. Does it actually look like the distribution of galaxies in the sky? And to a certain extent, the answer is yes, these are almost indistinguishable. And the same can be done with quasars, with active black holes. Actually, this is another image, but these blue ones are actually the quasars, these active black holes. And we can see them much far back in time. This white one is how far back we go just looking at galaxy. So looking at galaxy, we can only go back maybe 1 giga-year or so, or 2-3 giga-years. If we look at black holes, well, we can actually go back in time much more. We can see active black holes, as I said before, when the universe was still very young. And we can do a similar kind of things. Again, we can play in the computer, we can make a simulation. This is a simulation of a large part of the sky, again, done on a computer. And we can see how, as time passes by, galaxies that could be represented by these white spots get together, they get close to each other, they form an empty space. Galaxies get together, forming these groups of galaxies and leaving empty space around them. And when they get together with each other, they could activate a black hole. So we could estimate what would be the distribution in the sky of these black holes and compare it with observation. And that's something I've been working on, especially during my PhD. Now, one thing, where actually did these black holes come from? We don't know exactly, we can just speculate. They could either be the remnants of the first massive stars. So the first stars that formed when the universe was very young were probably much bigger than the stars that we see now, and they could have just ended their life and collapsed into a big black hole. Or they could form from large clouds of gas. If you imagine a huge collection of gas that just collapses at once into a single black hole, if the physical conditions are good enough, or they could form a collection of stars that is so compact that eventually these will also collapse into a big black hole. This just quickly to give you an idea of the research that is done also here. There's an image from a simulation from some people here. This is just what we would look, one of the first stars as it exploding, and this star that is now exploding could die into a black hole. But there is a problem here. This black hole still would not be that big. It would just be 100 times maybe the mass of the sun. But the point is that we see black hole, I come back to this, when the universe was really young. So there might not have been enough time to get so big. So another option is this option of the forming from a large cloud of gas. And this is something I've been working on in collaboration with people in Zurich. When I was in Zurich, the idea that actually you could form a large cloud of gas, even in the interaction of two galaxies, and you could form a black hole in one go from this just collection, a black hole even of just at once, a black hole of 1,000,000 times the mass of the sun. So we saw that black holes exist, supermassive, we call them supermassive black holes. These black holes that are 1,000,000 or 1,000,000,000 times the mass of the sun, they exist. We know they exist because they're active, or because, like in the case of our Milky Way, we see the influence of them on the stars around. Now astronomers know that there is a very strong relation between the black hole and the galaxy in which they live. which they explain with the fact that they could be born in the same event, this merger, which gives a lot of this galaxy getting together. They give a lot of fuel to the black hole, a lot of food, and the black hole shines and eventually affects the whole galaxy and creates galaxies as we see them today. And we looked briefly at how they could form. They could either come from very massive star or the collection directly of the direct collapse of gas, of a lot of gas. Now, before I finish, just give me 2 more minutes just to tell you that the future of black hole research is really bright, even brighter than today. So, not only now we have more and more powerful telescopes that could see more and more of these active black holes, but there is something very interesting that is going to happen that you might see in the news in the next few months. Astronomers have found, so this crosses the position of the black hole at the center of our galaxy, and this arrow is pointing to a cloud of gas that, as you follow year by year, is getting closer and closer to the black hole. So compare, for example, in 2002, it was this far. Now in 2011, we got this close. This looks like it's a ball of gas that is getting closer to where we think the black hole is. And eventually, some of this gas might get trapped by the black hole, and the black hole might start shining. Our own black hole in our galaxy might start shining. It will not have consequences for us, but it might make something nice or pretty that we could see in the sky. I'm not sure if we could just see it with our eyes, but certainly with some special telescope. And this could be, again, a great proof of the existence of a black hole in our galaxy. This is a nice animation pointing at the black hole is at the center. This is this ball of gas that is getting closer. You get 2013, it gets ripped. Part of it gets escaped, and part of it is getting on the black hole, and the black hole shines. It's sort of like they call it like a snack. It's a snack for the black hole. It's not much, but it's just something to satisfy its appetite for a bit. And so this is interesting because it could happen soon. It could be in the news. So we're in a very lucky moment to actually have a proof of the existence, again, of a black hole. And another really cool thing that could happen in the next 10 years, hopefully, is, well, what happens when two galaxies get together, if each of them has a black hole, such a big black hole at the center, these black holes could both light up. And actually, this is a real image of two galaxies that are getting together, and we actually see two active black holes at the same time, two black holes active at the same time. Eventually, these two black holes could become one themselves. This is a simulation, and this is just showing the distance between the two black holes during such what we call a merger. And first they're far away, then they sort of dance again around each other, they get closer and then further, and then closer and then further away, until they become so close that they could become one. For the first time, a few years ago, physicists, it's called numerical relativity. Physicists that do very complicated stuff that I don't understand. I wouldn't be able to do it, but they have been able to simulate, to give really a simulation in general relativity of what happens when two black holes get close to each other. And when these events happen, there are what they're called gravitational waves. So there are waves that are disturbance in the space-time, how Einstein defined it. And these waves are completely different from any kind of light we know. They are waves of gravity. And these waves could be observed. There is already a telescope of an observatory. They're called telescope, even though they're not like what we think of a telescope. This is an experiment, it's called LIGO, that has very complicated setting to detect any fluctuation that could come from these waves. But the most exciting one, which is not sure whether it will happen or not, because you need a lot of money to build it, is an experiment that would happen in space. It's called LISA, or NGO, New Gravity Observatory, something like that. And this will be 3 spacecraft sending laser to each other. And when the laser light, if there is one of these gravity waves passing by, this laser would arrive at the other spacecraft with a difference in time that is due to this wave. And with this difference in time, you can estimate what was the mass of the black hole that generated the wave, and even what was its spin. So amazingly, with such an observatory, you could really actually see black holes getting together for the first time. And this hopefully might happen in the last 10 or 20 years. So I just finish here, just one last slide. I have many nice friends and colleagues that came tonight to answer questions not only on black holes, they're happy to talk to you later, but also to other things. My partner, as I introduced before, he works on dark matter. Maria Giovanna Dainotti, she works on gamma ray burst, very energetic phenomena. Carlos Cunha works on dark energy. Rebecca Cunning, she works on black holes, very big black holes in clusters of galaxy. She's up here. Irina works also on galaxy clusters, so collection of galaxy, in particular on the turbulence and the gas that is in this cluster, or weird things going on. And Julie, she works on the most massive black holes. She has been studying and finding really big black holes. So later, I encourage you later to talk to them too. Thank you.
Well, Silvia, thank you very much. We have time for some questions. So please raise your hand, and these kind ladies in the front will run a microphone up to you. We'll start here. And please wait until you get the microphone to ask the question so that the questions can be recorded along with the answers. So, please.
These active black holes with the X-ray jets must have significant magnetic fields associated with them, do they not?
That's really true. That's a very good point. Actually, sorry, I didn't say that. All these really very big and long jets that you see that are so strong that can even get out of the old galaxy are powered by magnetic fields that form in this accretion disk. So it's the magnetic field that is able to accelerate some particles, electrons and protons, to these very high speeds. Yeah, thank you.
Okay, please.
Are black holes being formed now? And if they are, how long do they take to form? And can we observe them?
That's another good point. So black holes that come from stars certainly are forming now. We can see them in gamma ray bursts. Somehow gamma ray bursts are the, maybe you can call it the smoking gun of a black hole forming. But these are the small black holes, the stellar black holes, the ones that come from the end of a star. These huge black holes, these massive black holes at the center of galaxies, is not clear whether they could form now. Actually, from a work that I've done recently, we speculate that there could be some condition for the formation of them in some weird, some strange region of the universe, like where there are some special conditions. For example, if there is a galaxy that doesn't already have a black hole, one of these big black holes at the center, if you get an event like one of these mergers that can get a lot of gas in the center, maybe this gas could collapse in one go into a black hole. Now, whether you could really see that, we're still working on it, trying to think if that's possible. It's not clear yet. Yeah.
Okay.
Actually, I was wondering, at the point of Big Bang, since the whole universe was supposedly condensed in a point, how come the whole thing didn't collapse into a black hole?
Sorry, say it again?
I was wondering, at the point of Big Bang, since supposedly the whole universe was condensed at a point, how come the whole thing did not collapse into a black hole?
Oh, that's a tough question. Well, what we know is that soon after the Big Bang, there was this phase called inflation. That it's complicated. It started from, it's described by the physics, we know it. It was an explosion, right? Big Bang was somehow we can see it as an explosion. And soon after that, we think that there was this phase called inflation in which the universe got incredibly bigger in a snapshot, much less than a time that we could, less than a second. And with this happening, there was no way for everything to collapse. That's all I can say. Maybe we can discuss more later. I think about it. Thanks.
When a star collapses into a black hole, the star has lots of helium, I guess, and some hydrogen left over or whatever. What happens to those atoms? Do they all become subatomic particles and all smashed together in a little tiny bunch, or?
So when you get to this stage, the stars have already essentially finished all their hydrogen, already burned it all into helium. The helium has been burned into carbon, oxygen, and so what happens is there are different transitions because so what happens is stars doesn't have fuel anymore to burn, so it shrinks, and then there is a shock and explodes, and during this part of it gets ejected away, and part of it goes back, and finally it's not anymore in the form of element as we think, hydrogen. It's just particle, primordial, protons, electrons, neutrons, and they just get together and they form.
It's one of the biggest questions in physics. What happens when particles go down the center of a black hole? Are they quarks? Are they strings? Nobody knows. It's too small. It's beyond our experimental reach. Maybe we'll get there someday, but not yet. Other questions?
This one here? Oh.
Please.
I have a question about the nature of observation in deep space. How do you, when you watch the evolution of an event in deep space, how do you correct for the fact that we're on a moving reference frame and that what we're seeing is not actually the motion of the object itself, and it's got to do with our motion in space?
Yeah, so now we have a very good understanding on how we move, just by looking at some reference points, so we know how fast we move. So we just somehow, astronomers just subtract that motion into what you see the motion of the other object that you're looking at. So you can correct for that. There are ways to correct for that. So then you actually get out what is really the motion of the object you're looking at. And you can see galaxies that are going far away from us, other galaxies that are getting close to us. And you can get how far a galaxy is just by looking how fast it's going away.
There's one up there. And then let me ask, there are lots of young people in the audience. If any of you kids want to ask a question, the floor will be open after this question.
Does the black hole contain dark matter? And if so, is it in the same proportion as dark matter within its universe? I mean, within its galaxy?
I'm sorry, I'll have to ask you to repeat because I didn't hear.
My question is about whether the black hole contains dark matter, and if so, if it's in the same proportion as dark matter within its galaxy.
It could contain dark matter because dark matter, as we think it works, it only interacts with things gravitationally. So in principle, if there is a dark matter particle, we don't know what that is, but if there is a dark matter particle really close to a black hole, as everything else, as gas or dust, it would get in. So there could be dark matter in a black hole. Whether it's in the same proportion, it might not be. So what astronomers think from experiments and simulation is that there is actually not much dark matter at the very center of a galaxy. So there is dark matter, but it's not that there is so much more than outside. So whether there would be much of dark matter inside black holes, I don't know. I don't know if it actually would be a significant contribution to our black hole. Yeah.
Okay, who's next?
In one of your early slides, you said that if the Earth were a black hole, it would be 0.3 inches. It was my understanding that black holes have zero volume and infinite density. Can you reconcile these notions?
When I say 0.3 inches, it would not be the size of the singularity of that point where all the mass is getting in, but would be, thanks for pointing that out because maybe that was not clear, that would be the radius of this, what we call event horizon. So if you go below this 0.3 inches, things would just fall in, and you wouldn't see what is happening and would now be able to escape. Now, everything that falls in, we cannot really explain. There is not a law of physics as we know it right now that could explain what happens. So we think everything is just going to the center in this point of singularity. It would just be, yes, infinitely dense, so with no volume, yes.
Thank you.
Okay. So let's just take 2 more questions here in the public session. Please go ahead.
With a gamma ray burst, how wide an angle is that coming from, and what sort of magnetic field is required to focus that to those angles?
I don't remember on top of my head what would be the power of the magnetic field. Maybe some of my colleagues that work on that would have an idea. Do you remember? I'll think about it, and we can.
And how wide an arc is it coming out in?
That depends, but it's pretty narrow. It's a pretty narrow cone. Again, I don't. You can see from this image, it's what, like 10 degrees maybe? Something like that. Yeah. There is a young guy there. Maybe we can get. Oh, sorry.
If light is a massless particle, how does it get affected by the gravity of a black hole?
Sorry?
If light is a massless particle, you know, photons, how is it affected by the gravity of a black hole?
That's a good point. Well, we know that light is without mass, but it is a particle. And so the point here is that it's not light that is getting in, it's mass, things that have mass that are getting in. But still, you would need, whatever is inside would need to be faster than the speed of light, to get out. So light,
Well, even light, if it falls in.
Right, sorry, yes, sure. The space is curved. I was just thinking about that. Yes, thank you. Yes.
Even light, if it falls in, those photons can't get out again.
Yes.
Okay.
Yes.
Last question then.
Yes. What happens to the 4 forces once you've entered a black hole? Have they coalesced into the primeval force that perhaps started the universe?
God knows.
Good answer.
Maybe that's a good note to end on. So let me now tell you what's going to happen. Those of you who have more questions, either you can come up and talk to Silvia, or some of her colleagues will be wearing these hats. So anyone who has a hat on claims some knowledge and might be able to answer your question. And you can find out. There'll be people out there with hats and people down here. And those are Silvia's colleagues from KIPAC, our astronomy institute here. The next thing is, probably there are some of you here who are from high school who need signatures, and come to me, I'll sign your papers. And the rest of you, I hope you've had a good time, and we'll see you again in 2 months for another one of these public lectures.